Imagine you're standing outside on a clear night looking upward. You look up at the sky. You see thousands of bright stars. The Milky Way stretches across the darkness in a river of light. It's beautiful. It's awe-inspiring. It feels infinite and overwhelming in its cosmic grandeur. But here's a deeply humbling truth. You're only seeing a tiny fraction of what's actually out there. You're only seeing the brightest objects nearby. You're only seeing the visible light, a narrow sliver of the electromagnetic spectrum. Most of the universe is invisible to your naked eye. The faint galaxies beyond what you can see, invisible. The nebulae hidden behind clouds of dust, blocked from your view. The most distant galaxies, whose light has been traveling for over 13 billion years. Too faint to perceive? The supernova explosions happening right now in distant galaxies? You'll never know they occurred. The infrared radiation from star-forming regions? Blocked by Earth's atmosphere, the X-rays from black holes and neutron stars, absorbed by the air around you. The universe is full of light and radiation at wavelengths your eyes can't detect and your instruments can't access from Earth. But what if you could see deeper? What if you could see light that's so faint it takes billions of years to reach you? What if you could see through cosmic dust and gas that normally blocks your view? What if you could see infrared light, ultraviolet light, X-rays and gamma rays that you can't see with your eyes? What if you could peer back in time to the early universe just a few 100 million years after the Big Bang to see how the first stars and galaxies were born? That's what space telescopes do. They're the most powerful instruments for astronomy that humans have ever built. They're machines orbiting above Earth, collecting ancient light from the distant universe, revealing secrets about the cosmos that have been hidden since the beginning of time. They've transformed astronomy from a science that observed only what our eyes could see to one that observes the entire electromagnetic spectrum. They've given us views of the universe that previous generations could never have imagined. They're some of the most powerful instruments humans have ever built. They've transformed our understanding of the universe. They've revealed things we never imagined existed. And they've cost billions and billions of dollars to build and launch. In this video, we're going to explore the world of space telescopes. We're going to talk about their history, their science, their discoveries. We're going to talk about their enormous costs and what we're getting for our money. We're going to look at the telescopes of the past, the ones operating right now, and the incredible missions coming in the future. And I think you'll be amazed at what we've learned and what we're about to learn using these incredible machines orbiting above Earth, looking deeper into space and further back in time than ever before. Let me start with a question. Why do we need space telescopes at all? Why not just build bigger and bigger telescopes here on Earth? The answer is the atmosphere. Earth's atmosphere is thick. It's full of water vapor, dust, gases. This atmosphere does a lot of good things. It keeps us alive. It protects us from radiation. It creates the weather that sustains life. But for astronomy, it's a problem. When light from distant stars and galaxies travels through the atmosphere, it gets distorted. The air currents bend the light, shimmer it, blur it. This is why stars twinkle when you look at them from Earth. The twinkling is caused by the atmosphere moving the light around. This twinkling is bad for telescopes. It limits how much detail they can see. No matter how big you make a telescope on Earth, the atmosphere will blur its view. There's a physical limit, the diffraction limit, that atmospheric distortion creates. You can only see so much detail. But in space, above the atmosphere, there's no distortion. Light comes straight from distant objects to your telescope without being bent by air. This means space telescopes can see more detail, can see fainter objects than Earth-based telescopes. They're not blocked by atmospheric distortion. Moreover, Earth's atmosphere blocks certain wavelengths of light. Ultraviolet light doesn't make it through. X-rays don't make it through. Gamma rays don't make it through. Most infrared light doesn't make it through. If you want to observe the universe in these wavelengths, you have to go to space. So space telescopes have two major advantages over Earth-based telescopes. They're not limited by atmospheric distortion, and they can observe wavelengths of light that don't reach the ground. Of course, they have disadvantages too. They're incredibly expensive to build and launch. They're hard to repair if something goes wrong. They have limited power, limited cooling capacity, limited space. Everything about space telescopes is challenging. But despite these challenges, space telescopes have been absolutely crucial to modern astronomy. They've revolutionized our understanding of the cosmos. Let me talk about the history. Understanding where space telescopes came from helps you appreciate what we have today. The idea of putting telescopes in space is actually quite old. In the early 1900s, even before Einstein developed relativity, astronomers understood that Earth's atmosphere limits how much detail telescopes can see. The twinkling of stars is caused by atmospheric distortion. If you could get above the atmosphere, you could see more detail. In 1923, Hermann Oberth, a rocket pioneer, published a paper discussing putting instruments on space stations. In 1945, Arthur C. Clarke, the science fiction author, published an article about geostationary satellites. He suggested that satellites in synchronous orbits around Earth could be used for communication and observation. But these were just ideas. The technology didn't exist. Rockets in the 1940s could barely reach the altitude of high-altitude aircraft. Getting to orbit required rocket technology that didn't exist yet. Then, after World War II, advances in rocket technology accelerated. Both the United States and the Soviet Union were developing intercontinental ballistic missiles. These missiles used rocket technology that could eventually reach orbital speeds. In 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. It was a simple sphere with radio transmitters, but it proved that satellites could be built and launched. The space age had begun. This triggered a flurry of activity. The United States launched Explorer 1 in 1958 and discovered the radiation belts around Earth. The USSR launched Luna spacecraft toward the Moon. Competition between the superpowers was driving space exploration forward. In the 1960s, as rockets became more powerful and spacecraft became more sophisticated, space agencies began launching scientific satellites. The earliest space telescopes were simple, basic instruments on spacecraft that orbited Earth. The Orbital Astronomical Observatory, OAO missions, starting in 1966, carried ultraviolet telescopes to space. They made observations in ultraviolet light that couldn't be made from Earth. These early missions proved the concept worked. You could put telescopes in space, they could operate for years, they could make valuable scientific observations. But they were small, crude, compared to what would come later. The next major step was the orbiting solar observatory missions and the Skylab missions in the early 1970s. Skylab, launched in 1973, was a space station that carried sophisticated solar telescopes and astronomical instruments. It made remarkable observations of the sun, of stars, and of galaxies. But Skylab had limited capabilities and operated for only about 6 years. The real revolution came with the Hubble Space Telescope. The idea for the Hubble started in the 1960s. Astronomers envisioned a large optical telescope in space, far larger than any instrument that could be launched at that time. The project was officially approved by NASA in 1972. The concept was ambitious: a 2.4-meter diameter telescope in orbit, capable of studying everything from nearby planets to the most distant galaxies. But building the Hubble was incredibly challenging. The technology had to be developed from scratch. How do you design a telescope to operate in the vacuum of space? How do you protect it from radiation and temperature extremes? How do you send commands to it across hundreds of kilometers? How do you receive the data it collects? The Hubble took years to design, develop, and build. Different institutions contributed different components. The optical tube assembly came from NASA's Marshall Space Flight Center. The mirror was made by Perkin-Elmer. Lockheed Missiles and Space Company built the spacecraft bus. Ball. Aerospace built science instruments. Universities and observatories conducted the science planning. The costs kept escalating. The initial budget was maybe $400 million. By the 1980s, the estimates had climbed. By the time the Hubble launched, the total cost was about $2.5 billion, making it one of the most expensive scientific instruments ever built at that time. And then came the launch date, April 24th, 1990. The Space Shuttle Discovery carried the Hubble into orbit at an altitude of 600 kilometers. For the first time, humanity had a large telescope looking at the universe from above Earth's atmosphere. But within hours, astronomers realized something was wrong. The images coming back weren't sharp. They were blurry. The Hubble's primary mirror had a defect. During manufacturing, the mirror had been ground to the wrong shape, a spherical aberration. The mirror focused light to different points depending on the wavelength. It was like having glasses with the wrong prescription. The most expensive telescope ever built was essentially blind. The space astronomy community was devastated. The press questioned why billions of dollars had been spent on a broken telescope. Congress questioned whether the project should be canceled. It was a crisis. But there was hope. The Hubble had been designed with the capability to be serviced by astronauts. Unlike most satellites, which are supposed to operate indefinitely without maintenance, the Hubble was built assuming it would need repairs and upgrades. The designers knew that in space things go wrong, and you need to be able to fix them. So NASA planned a servicing mission. On December 2nd, 1993, the Space Shuttle Endeavour launched toward the Hubble. On board were 7 astronauts, including Story Musgrave and Jeffrey Hoffman. Their mission was to repair the telescope in orbit. It was one of the most daring repair missions ever attempted. The astronauts had to do a series of spacewalks. They had to remove the old wide-field/planetary camera and install a new one with corrective optics built in, essentially glasses for the Hubble. They had to replace other components. They had to work in the vacuum of space, in bulky spacesuits performing delicate operations on a satellite moving at 28,000 kilometers per hour. But they succeeded. The repair mission was a triumph. The new wide-field/planetary camera with its corrective optics transformed the Hubble's vision. When the first clear images came back to Earth on December 18, 1993, they revealed a universe of stunning clarity. Galaxies that had appeared as blurry blobs in the earlier images now showed intricate structure. Stars appeared as distinct points rather than blurry halos. It was a miracle. Suddenly, the Hubble was the most successful space telescope ever built. Public support surged. Hubble images were featured in newspapers, magazines, on television. The telescope captured imaginations. Hubble images became iconic. The Eagle Nebula, the Pillars of Creation, the Deep Field. Over the next 2 decades, astronauts conducted 5 more servicing missions to the Hubble. Each mission repaired damage, replaced aging components, and installed new, more powerful instruments. The Wide Field Camera 3, installed in 2009, gave the Hubble even more capability. The Cosmic Origin Spectrograph and the Space Telescope Imaging Spectrograph gave it the ability to analyze light in unprecedented detail. The Hubble kept operating year after year, decade after decade. It was supposed to have a 15-year lifespan. It's now been operating for over 30 years. It continues to make discoveries. The Hubble became more than just a scientific instrument. It became a symbol of human capability, of our ability to build extraordinary machines and send them into space. It became an inspiration to scientists and the public alike. Then, in 1972, NASA approved a project that would become the most famous space telescope of all time, the Hubble Space Telescope. The project started in the 1970s. The scope of it was enormous. They wanted to build a telescope that would be 2.4 meters in diameter, the largest telescope in space at that time. They wanted it to be in a stable orbit where it could observe for years, decades. They wanted it to be sophisticated enough to study everything from planets in our solar system to the most distant galaxies in the universe. The Hubble Space Telescope took years to build. It was incredibly expensive, eventually costing about $2.5 billion, adjusted for inflation. It faced technical challenges, budget overruns, schedule delays. But finally, on April the 24th, 1990, the Space Shuttle Discovery launched the Hubble Space Telescope into orbit. And then something went wrong. The first images came back blurry. The primary mirror had a flaw. It had been ground to the wrong shape. The mirror had a spherical aberration, a defect that made images out of focus. It was one of the most expensive mistakes in the history of science. The project that was supposed to revolutionize astronomy produced blurry images. But this is where the story gets interesting. NASA had designed the Hubble with the ability to be serviced. Unlike most satellites, which are supposed to operate forever without maintenance, the Hubble was designed so that astronauts could repair it, upgrade it, replace parts. So, in December 1993, the Space Shuttle Endeavour launched. 7 astronauts went up to the Hubble. They performed a repair mission. They installed corrective optics, basically glasses for the Hubble, that fixed the aberration. It was one of the most daring and difficult repair missions ever attempted. But it worked. Suddenly, the Hubble was seeing clearly. The first clear images came back, and they were stunning. They revealed details of galaxies, nebulae, and stars that had never been seen before. The Hubble became a sensation. The public fell in love with Hubble images. Scientists made breakthrough discoveries. The Hubble Space Telescope became perhaps the most famous scientific instrument in history. Over the decades, astronauts went up to the Hubble multiple times. They repaired it, upgraded it, replaced instruments. Each servicing mission extended the Hubble's life and improved its capabilities. The telescope that was supposed to operate for 15 years has now been operating for over 30 years. And the Hubble has made some of the most important discoveries in the history of astronomy. It measured the expansion rate of the universe, which led to the discovery of dark energy. It observed the most distant galaxies, allowing us to see the early universe. It provided evidence for supermassive black holes at the centers of galaxies. It showed us that planetary systems around other stars are common. The Hubble's contributions to our understanding of the cosmos are almost impossible to overstate. But the Hubble isn't the only space telescope. There are others, many others. Let me talk about some of the most important ones. The Chandra X-ray Observatory was launched on July 23, 1999, on the Space Shuttle Columbia. It was named after Subrahmanyan Chandrasekhar, a brilliant Indian-American astrophysicist who made fundamental contributions to understanding stellar evolution. The Chandra telescope is about the size of a bus and weighs about 4,760 kilograms. It's designed to observe X-rays, high-energy light with wavelengths 1,000 times smaller than visible light. X-rays are produced by extremely hot or extremely energetic objects. When material falls into a black hole and gets heated to millions of degrees, it emits X-rays. When neutron stars spin and emit jets of particles, those jets produce X-rays. When supernova explosions heat gas to extreme temperatures, the gas emits X-rays. When galaxy clusters contain hot gas between galaxies, that gas emits X-rays. Chandra can observe these X-rays because it's in space. X-rays are absorbed by Earth's atmosphere, so they can't be observed from the ground. You have to go to space. Chandra has made remarkable discoveries. It's observed supermassive black holes at the centers of galaxies and measured the rate at which they consume material. It's observed supernova remnants, the remains of stellar explosions, revealing details about how stars die. It's observed neutron stars and measured their properties. It's observed the hot gas in galaxy clusters and discovered that the universe's largest structures are held together by gravity. Chandra has been operating for over 25 years now. It was built to last about 5 years. Like Hubble, it has far exceeded expectations. It continues to make discoveries today. The Spitzer Space Telescope was launched on August 25, 2003. It was named after Lyman Spitzer Jr., an astronomer who proposed the idea of space telescopes in the 1940s, decades before they became reality. Spitzer observes infrared light. Infrared light has longer wavelengths than visible light. It's the kind of light that warm objects emit. If you look at the universe through infrared eyes, you see the warm gas and dust in star-forming regions. You see newborn stars still embedded in their birth cocoons of dust. You see warm planets around other stars. You see distant galaxies that are so far away their light has been redshifted into the infrared. Spitzer couldn't observe from Earth because Earth's atmosphere is opaque to most infrared light. So it had to go to space. Moreover, Spitzer itself emits infrared light because it's warm. To observe infrared light, it needs to be very cold, colder than the objects it's observing. So Spitzer carried about 360 kilograms of super cold liquid helium to cool its instruments to a temperature of about 1.4 Kelvin, colder than outer space. Spitzer made remarkable discoveries. It observed star-forming regions in stunning detail. It discovered that planets are common around other stars. It provided the first detailed observations of the most distant galaxies. It studied the structure and composition of planetary atmospheres in exoplanet systems. Spitzer was supposed to operate for about 2.5 years, but it continued operating far longer, for over 16 years. In 2009, it ran out of the liquid helium cooling fluid. Without the coolant, some of its instruments couldn't operate, but 2 channels of its infrared array camera could still work using passive cooling. So Spitzer continued observing, though with diminished capabilities. Finally, on January 30th, 2020, Spitzer was shut down. NASA could no longer operate the telescope safely. It had made its last observation. Over its 16-year mission, Spitzer had revolutionized infrared astronomy. There are many other space telescopes, each making important contributions to our understanding of the universe. The Compton Gamma Ray Observatory operated in the 1990s, observing gamma rays, the highest energy form of light. Gamma rays are produced by the most violent and energetic phenomena in the universe. When atoms and particles annihilate, they produce gamma rays. When supernovae explode, they produce gamma rays. When black holes accrete material, they produce gamma rays. Compton revealed that the gamma-ray universe is populated with sources we had never imagined. It discovered over 400 gamma-ray sources and revolutionized our understanding of high-energy astrophysics. The XMM Newton Observatory, launched by the European Space Agency in 1999, has been observing X-rays for over 2 decades. XMM stands for X-ray Multi-Mirror Mission. It has 3 mirrors that focus X-rays from distant sources onto detectors. XMM Newton has discovered countless black holes, neutron stars, and other exotic objects. It has measured the properties of hot gas in galaxy clusters. It has studied the atmospheres of planets. Its observations have deepened our understanding of the X-ray universe. The SWIFT satellite, launched in 2004, specializes in observing gamma-ray bursts, brief flashes of gamma rays that can be brighter than supernovae but last only seconds to minutes. SWIFT can rapidly detect a gamma ray burst and point its instruments at the afterglow to observe it at multiple wavelengths. SWIFT's observations revealed that gamma ray bursts are caused by either the collapse of massive stars or the collision of 2 neutron stars. It has discovered and studied thousands of gamma-ray bursts, revealing their properties and origins. Gamma-ray bursts are among the most violent events in the universe, and SWIFT has given us unprecedented insight into them. TESS, Transiting Exoplanet Survey Satellite, launched in 2018, observes visible light from hundreds of thousands of stars searching for planets. It detects planets by observing the tiny dips in starlight when a planet passes in front of its star. A transit. By monitoring thousands of stars constantly, TESS has discovered thousands of exoplanets. It's continuing to find new worlds and has become one of the most prolific exoplanet discovery machines we have. The Akari Infrared Space Telescope, a Japanese mission, operated from 2006 to 2011. Though it had a shorter operational life than some other telescopes, it made important infrared observations. The WISE, Wide Field Infrared Survey Explorer mission, launched by NASA, surveyed the entire sky in infrared. It discovered thousands of new objects, including the nearest star to us, other than the Sun. The Suzaku X-ray Observatory AWI, Japanese mission, operated from 2005 to 2015. It made detailed X-ray observations of galaxy clusters, active galactic nuclei, and other high-energy sources. The Integral Gamma Ray Observatory, operated by ESA, has been observing gamma rays since 2002. It studies gamma ray sources including black holes, neutron stars, and pulsars. Each of these telescopes specialized in observing a particular wavelength or type of phenomenon. Together, they've painted a comprehensive picture of the universe across the entire electromagnetic spectrum. The legacy of these missions is enormous. They've discovered thousands of objects. They've revealed phenomena we never imagined. They've answered fundamental questions about the universe. Behind these missions are remarkable scientists who had the vision to imagine what could be discovered. John Mather and George Smoot won the Nobel Prize in Physics in 2006 for their work with the Kobe satellite, which measured the cosmic microwave background, the afterglow of the Big Bang. Arno Penzias and Robert Wilson won the Nobel Prize for accidentally discovering this same cosmic microwave background radiation in 1964. Martin Schmidt discovered quasars and provided evidence that the universe contained objects far more distant and luminous than anyone had imagined. Edwin Hubble himself provided evidence that galaxies exist beyond our own Milky Way, and that the universe is expanding. These scientists had courage. They asked questions others hadn't thought to ask. They made observations that challenged conventional wisdom. They persevered through obstacles. Their work, combined with the space telescopes that followed, transformed our understanding of the cosmos. The story of space telescopes is the story of human determination, ingenuity, and curiosity. It's the story of astronomers asking fundamental questions about the universe. It's the story of engineers building remarkable machines to answer those questions. It's the story of international cooperation toward ambitious goals. Every space telescope mission represents thousands of people working toward a common goal. Teams of scientists who designed the scientific observations. Teams of engineers who designed and built the instruments. Teams of technicians who assembled and tested everything. Teams of managers who coordinated the projects. Teams of programmers who wrote the software. Teams of support staff who maintained the operations. When a space telescope succeeds and makes discoveries, it's a triumph for all these people. When a mission faces challenges or failures, these are shared across the teams. But the drive to understand the universe pushes everyone forward. This is what makes space telescopes so remarkable. They're not just scientific instruments, they're collective human achievements. They represent what we can do when we work together. And they've opened new questions. Every discovery raises new questions. Every observation reveals new mysteries. That's the beauty of science and astronomy. The pursuit of knowledge never ends. There's always more to discover, always new frontiers to explore. Let me reflect on some of the most transformative discoveries space telescopes have enabled. The discovery of dark energy changed how we understand the fate of the universe. Before Hubble observations of distant supernovae in the 1990s, astronomers assumed gravity would eventually slow the cosmic expansion and reverse it. But the observations showed the expansion is accelerating. Something, dark energy, makes up 68% of the universe. We still don't know what it is, but knowing it exists has changed everything. The discovery of supermassive black holes at galaxy centers revealed a profound connection between black holes and galaxies. Hubble observations of our galactic center showed stars orbiting an invisible massive object, Sagittarius A star, a 4 million solar mass black hole. Similar observations in many galaxies revealed that supermassive black holes are universal. They regulate galaxy formation and evolution. The discovery of thousands of exoplanets changed our understanding of planets. We learned planets are common. Essentially, every star has them. This means potentially habitable planets likely exist in vast numbers. The search for life is no longer a search for the rare, but among countless possibilities. The discovery of the accelerating expansion rate of the universe, confirmed by multiple independent observations, provided evidence for dark energy. This discovery was so significant it won the 2011 Nobel Prize. It fundamentally changed cosmology. The discovery that stars form efficiently throughout the universe showed that the cosmos is a vibrant place of creation. Stars are being born constantly in countless galaxies. Planets form around these stars. The universe is dynamic, evolutionary, filled with ongoing processes. These discoveries show the power of space telescopes. They reveal truths we wouldn't discover otherwise. They transform how we understand reality. They show that the universe is stranger and more wondrous than we imagined. The data from all these missions continues to produce discoveries. Astronomers analyze years-old data and make new discoveries. Papers are published using Hubble data from 20 years ago. Data from missions that have ended continues to be analyzed and studied. This is why space telescope data is preserved in archives, because the value of the data extends far beyond the original mission. These space telescope missions represent humanity's curiosity at its finest. They represent our drive to understand the universe. They represent the incredible achievements of science and engineering. There are many other space telescopes. The Compton Gamma Ray Observatory operated in the 1990s, observing gamma rays, the highest energy form of light. When atoms and particles annihilate, they produce gamma rays. When supernovae explode, they produce gamma rays. When black holes accrete material, they produce gamma rays. Compton observed these gamma rays and revolutionized our understanding of high-energy phenomena in the universe. The XMM Newton Observatory, launched by the European Space Agency in 1999, has been observing X-rays for over 2 decades. It's discovered countless black holes, neutron stars, and other exotic objects. The SWIFT satellite, launched in 2004, specializes in observing gamma ray bursts, brief flashes of gamma rays that can be brighter than supernova, but last only seconds to minutes. SWIFT has discovered and studied thousands of gamma ray bursts, revealing their properties and origins. TESS, Transiting Exoplanet Survey Satellite, launched in 2018, observes visible light from hundreds of thousands of stars. It searches for planets around these stars by detecting the tiny dips in starlight when a planet passes in front of its star. TESS has discovered thousands of exoplanets. There are many more: the Akari Infrared Space Telescope, the WISE Infrared Survey Mission, the Suzaku X-ray Observatory, the Integral Gamma Ray Observatory. Each telescope observes a different wavelength. Together, they give us a complete picture of the universe across the entire electromagnetic spectrum. But then, in the 2000s, a new space telescope was being built that would eventually surpass the Hubble in power and capability. It was called the James Webb Space Telescope. and its story is one of the most remarkable and expensive stories in the history of science. The James Webb Space Telescope, or JWST, started as a concept in the mid-1990s. NASA and the European Space Agency began thinking about what should come after Hubble. The idea was ambitious: build a space telescope that would be more powerful than Hubble, make it much larger, about 6.5 meters in diameter compared to Hubble's 2.4 meters. Make it observe primarily infrared light, which would allow it to see even more distant galaxies, to see through dust clouds that block visible light, and to observe the earliest galaxies in the universe. Make it powerful enough to study the first galaxies that formed, just 100 million years after the Big Bang. The original concept was developed by NASA engineer and scientist John Mather and James Webb, a former NASA administrator. The idea was to create a next-generation space observatory that would be a flagship mission for astronomy. But here's where the story gets complicated: the costs. As the project developed through the late 1990s and 2000s, the estimated costs kept escalating. And I mean kept escalating. The original estimate in the mid-1990s was maybe $500 million. By 2000, it had grown to about $1 billion. By 2005, estimates were around $3 billion. By 2010, they were at $6 billion. By 2015, Congress had approved a cost cap of $8 billion. By 2018, estimates were approaching $9 billion, and by the time of launch, the total cost had reached approximately $10 billion. This made the JWST the most expensive scientific instrument ever built. It surpassed the Hubble, which had cost about $2.5 billion in its era. The JWST became more expensive than the International Space Station, which cost about $150 billion, but was built over decades with multiple nations contributing. These cost overruns were controversial. Congress held hearings. Scientists debated whether the money was justified. Some argued that the funds would be better spent on other projects or on additional space telescopes rather than one massive observatory. There was serious discussion about canceling the project. But supporters of the JWST argued that it was necessary. They argued that the science it would enable was worth the cost. They argued that it was the natural next step after Hubble. They argued that it would answer fundamental questions about the universe. The delays also became notorious. The JWST missed its originally planned launch date of 2007, then 2011, then 2018. The launch kept getting pushed back. Sometimes it was technical issues. Sometimes it was design changes. Sometimes it was budget problems. By the time it actually launched, the project had been in development for over 2.5 decades. But finally, on December 25th, 2021, Christmas Day, the James Webb Space Telescope launched on a European Ariane 5 rocket from Kourou, French Guiana. It was one of the most dramatic and anxiety-provoking launches in space history. Everyone involved knew the stakes. Unlike the Hubble, which was launched on the space shuttle and could be repaired by astronauts, the JWST is located at Lagrange Point 2, a gravitational point about 1.5 million kilometers from Earth, where the Sun's gravity and Earth's gravity balance. It's too far away for any spacecraft to reach and repair. The JWST had to work perfectly from launch onwards. There would be no second chance. The launch itself was smooth, but what came next was terrifying for the project team. The JWST is an incredibly complex machine. After launch, it had to unfold. The sun shield, which was folded during launch, had to unfold in space. The mirror segments, which were folded, had to unfold and align perfectly. The instruments had to power up and be calibrated. Each step was a potential point of failure. If the sun shield didn't unfold correctly, the telescope would get too warm and stop working. If the mirror segments didn't align, the images would be blurry. If the instruments didn't power up, the mission would be a failure. Over the first month after launch, the JWST underwent a nail-biting series of deployment procedures. Mission control teams in Baltimore watched anxiously as each step was executed. The sun shield deployed successfully. The mirror segments unfolded. The instruments powered on. Each success was met with cheers from the control room. Then came the calibration phase. Over the following months, the JWST's instruments were carefully calibrated and tested. Light was collected from stars and used to focus the telescope. The instruments were tested to ensure they were working properly. And finally, in the summer of 2022, about 6 months after launch, the first full-resolution images were released to the public. They were breathtaking. They were stunning. They were transformative. The first image was the Hubble Ultra Deep Field equivalent, an image of a region of sky in the constellation Carina. It showed thousands of galaxies. Many of them were very distant, so distant that their light had been traveling for over 13 billion years. These were images of the early universe, showing galaxies as they were just a few hundred million years after the Big Bang. Another image showed the Pillars of Creation, a star-forming region in the Eagle Nebula, with clarity and detail that far surpassed any previous observation. You could see individual stars being born, see the structure of the gas and dust clouds. Another image showed Neptune, revealing details of its atmosphere that had never been seen before. You could see storms, wind patterns, clouds. Another image showed the spectrum of light from an exoplanet's atmosphere, direct detection of molecules like water and methane in the atmosphere of a planet orbiting another star. This had been done before, but never with such clarity and detail. The images were released to tremendous acclaim. The public was amazed. Scientists were stunned. The JWST had exceeded all expectations. Since those first images, the JWST has continued to make remarkable discoveries. Astronomers used the JWST to observe galaxies that formed only 200 to 300 million years after the Big Bang. Before the JWST, the most distant galaxies known were from about 400 to 500 million years after the Big Bang. Suddenly, we were seeing even more distant, even earlier galaxies. These distant galaxies were surprisingly large. According to previous models, galaxies shouldn't have been able to grow so large so quickly. The discovery of these large early galaxies means that either our understanding of galaxy formation is incomplete, or the early universe was different from what we thought. The JWST has observed the aftermath of a gamma-ray burst, a brief, violent explosion that can be brighter than a supernovae. It has observed the jets of material being expelled by black holes. It has studied star-forming regions in detail, watching how stars and planetary systems are born. It has characterized the atmospheres of exoplanets, finding water, methane, carbon dioxide, and other molecules. It has even found evidence of complex organic molecules in exoplanet atmospheres. These are compounds that could potentially be related to life. The JWST has observed gravitationally lensed galaxies, distant galaxies whose light is bent and magnified by the gravity of massive objects in front of them. This magnification allows us to see details in these distant galaxies that would otherwise be too faint to detect. The JWST has revolutionized our understanding of the early universe. It's shown that the universe's history is more complex than we thought. Galaxies formed faster and grew larger than expected. Star formation was more efficient in the early universe, and the JWST is still operating. It's probably going to continue operating for another decade or more, far longer than its original 5 to 10-year mission plan. Every observation it makes reveals something new about the universe. Every discovery raises new questions. When you consider all the discoveries the JWST is making and all the discoveries it will make in the future, the $10 billion price tag starts to seem more reasonable. This single telescope is transforming our understanding of the cosmos. It's answering fundamental questions. It's opening new frontiers in astronomy. The JWST has proven that the investment was worth it. But let me talk more about the costs of space telescopes, because the costs are enormous and it's worth understanding where the money goes. Building a space telescope is incredibly complex. You need a primary mirror made of special glass that's ground to a specific shape. For the Hubble, the primary mirror is 2.4 meters wide. For the JWST, the primary mirror is 6.5 meters wide, but it's made up of 18 individual hexagonal segments made of beryllium coated with gold. Making these mirrors is not easy. The tolerance has to be extremely tight. The surface has to be smooth to within billionths of a meter. Getting that kind of precision is difficult and expensive. The JWST's mirror cost hundreds of millions of dollars. Then you need the instruments, cameras, spectrographs, detectors. These are incredibly sophisticated pieces of equipment. They have to operate in the vacuum of space. They have to be protected from radiation and micrometeorites. The instruments on the JWST cost over $1 billion. You need a spacecraft bus, the structure that holds everything together. You need reaction wheels and gyroscopes to control the telescope's orientation. You need solar panels or nuclear batteries to power it. You need a communication system to transmit data back to Earth. All of this has to be incredibly reliable because you can't send a repairman into space. You need a launch vehicle. The JWST launched on an Ariane rocket which cost tens of millions of dollars per launch. The Hubble launched on the Space Shuttle, which cost hundreds of millions of dollars per mission. Just getting your telescope into space is a huge expense. And you need the people, thousands of engineers, scientists, technicians, project managers. You need ground stations to communicate with the telescope. You need supercomputers to process the data. All of this costs money. So when you add it all up, the total cost of a major space telescope can easily reach billions of dollars. The Hubble cost about $2.5 billion. The JWST cost about $10 billion. Chandra cost about $1.5 billion. Future space telescopes will cost billions more. Now you might ask, is it worth it? Is spending billions of dollars on space telescopes a good use of money? There are different ways to answer that question. From a pure cost-benefit analysis, it's hard to justify. That money could be spent on education, on medicine, on poverty reduction, on climate change. These are all important causes. But consider what we get for that money. The Hubble revolutionized astronomy. It fundamentally changed our understanding of the universe. The discoveries it made are priceless. They've inspired millions of people. They've led to new technologies. They've deepened human knowledge. The JWST is doing the same thing. It's revealing the universe in ways we never imagined. It's answering fundamental questions about how the universe began, how galaxies formed, whether life exists around other stars. Moreover, the money spent on space telescopes goes back into the economy. It pays salaries for engineers and scientists. It supports manufacturing facilities. It drives innovation in optics, materials, science, computer technology. Many technologies we use today were developed for space telescopes. Things like precision manufacturing, advanced materials, communication systems. So while the costs are enormous, the return on investment, both in terms of knowledge and economic benefit, is also enormous. Let me talk more about the science. How do space telescopes actually work? And why do different telescopes observe different wavelengths? Before we talk about light itself, let me explain why we need multiple telescopes observing different wavelengths. Imagine you wanted to understand a city. You could walk through it and observe with your eyes. You'd see buildings, streets, people, but you'd only get information from visible light. You wouldn't understand what's happening underground or inside buildings. You wouldn't understand the electrical and plumbing systems or the radio and cell phone signals flowing through the air. To get a complete understanding, you'd need multiple perspectives: satellites above, thermal imaging, ground penetrating radar, radio signal measurements. Similarly, if we only observe the universe with visible light, we get an incomplete picture. With infrared light, we see warm objects hidden in dust clouds, stars being born, distant galaxies, exoplanets. With ultraviolet light, we see very hot objects, hot stars, supernovae explosions. With X-rays, we see the most extreme objects, black holes, neutron stars, hot gas in galaxy clusters. With gamma rays, we see the most violent explosions, gamma ray bursts, jets from supermassive black holes. By observing the same object at multiple wavelengths, we get a complete picture. We understand what's happening. This multi-wavelength approach has been revolutionary. Every major discovery in the last few decades has involved observations at multiple wavelengths. Now let me talk about how light itself works. Light is an electromagnetic wave. It travels at a constant speed through vacuum, about 300,000 kilometers per second. But different types of light have different wavelengths. Visible light, the light your eyes can see, has wavelengths from about 400 nanometers, blue light, to about 700 nanometers, red light. A nanometer is 1/billionth of a meter, but visible light is only a tiny fraction of the electromagnetic spectrum. Beyond the red end of visible light is infrared light, with longer wavelengths. Beyond infrared is microwave radiation and radio waves, with even longer wavelengths. On the other side of visible light, beyond the blue end, is ultraviolet light, then X-rays, then gamma rays, with progressively shorter wavelengths. Different objects in the universe emit different types of light. Cool objects emit infrared light. Hot objects emit visible light and ultraviolet light. Very hot objects emit X-rays. Extremely energetic objects emit gamma rays. So if you want to study the full diversity of objects in the universe, you need to observe all these different wavelengths. You can't just use one telescope, you need multiple telescopes, each specialized to observe a particular wavelength. The Hubble primarily observes visible light and ultraviolet light. This allows it to see stars and galaxies in colors similar to what our eyes would see if they were powerful enough. The Spitzer observed infrared light. This allowed it to see through dust clouds that block visible light. It could observe star formation regions, young galaxies, and planets around other stars. The Chandra observes X-rays. This allows it to study the hottest objects in the universe: black holes, neutron stars, supernova remnants, hot gas in galaxy clusters. The JWST observes primarily infrared light, but also some visible light. It's particularly good at observing distant galaxies whose light has been redshifted into the infrared. So together, these telescopes give us a complete view of the universe across the entire electromagnetic spectrum. Let me explain in more detail how space telescopes collect and detect light, because it's fascinating to understand the technology. A space telescope's primary mirror collects light and focuses it. The mirror is curved, usually spherical or parabolic, so that parallel rays of light from a distant object are focused to a point. At this focal point, called the focal plane, instruments are placed to detect and analyze the light. The detection is done by sophisticated cameras and spectrographs. Modern cameras use detectors called CCDs, charge-coupled devices, or more recently, CMOS sensors. These devices are similar to the sensors in digital cameras, but far more sensitive. They're designed to detect individual photons, individual packets of light. When a photon hits the detector, it transfers its energy to an electron in the semiconductor material of the detector. This creates an electric charge that can be measured and recorded. By detecting many photons and counting where they land on the detector, a two-dimensional image can be created. These detectors are incredibly sensitive. A good astronomical detector might detect 90% of the photons that hit it. They can detect wavelengths from ultraviolet through visible to near infrared. For longer wavelength infrared light, different types of detectors are used, such as bolometers that detect the heat from photons. The key to sensitivity is low noise. In a perfect detector, the only signal would come from photons from the object being observed. But real detectors have noise, random electrical fluctuations that create false signals. To minimize noise, detectors are cooled to very low temperatures. For visible and near ultraviolet detectors, cooling to about 240 Kelvin minus 33 degrees Celsius is sufficient. For infrared detectors, cooling to 40 Kelvin or even lower is needed. At these temperatures, the thermal motion of atoms is minimized, reducing noise. The JWST uses a cryogenic system with multiple stages of cooling. A sunshield protects the instruments from the sun. Multiple layers of insulation and active cooling systems keep the instruments at the required temperatures. Once the photons are detected, the data is read from the detector and stored on board the spacecraft. The data is then transmitted to Earth. The transmission rates are limited by the power available and the communication system, so data is either stored and sent periodically or compressed before transmission. At ground stations on Earth, the data is received and processed. Raw data undergoes calibration, removing instrumental effects, correcting for detector artifacts, combining multiple exposures. The calibrated data is then made available to astronomers around the world. Scientists download the data and analyze it using computers and specialized software. They create images, extract spectral information, search for specific objects or phenomena. The power of having the raw data available is that new discoveries can be made from old data. An astronomer might download Hubble data from 20 years ago and make a new discovery that the original observers didn't see. This is one of the beautiful aspects of space telescope data. It's preserved and made available to the entire scientific community. Major observatories like Hubble and JWST have policies that make data publicly available after an initial period of exclusive access to the observers who requested the observation. This means discoveries can be made by anyone with access to a computer and the curiosity to analyze the data. The amount of data produced by space telescopes is enormous. The Hubble produces about 100 gigabytes of data per day. The JWST produces comparable or larger amounts. Over decades of operation, space telescopes produce petabytes of data. That's millions of gigabytes. Storing all this data requires enormous data centers. NASA maintains the Mikulski Archive for Space Telescopes, MAST, at the Space Telescope Science Institute. This archive stores data from many space telescopes. Scientists access this archive to download data for analysis. The processing and storage of space telescope data represents a significant ongoing cost. But it's an investment that pays off. Data from 20-year-old observations continues to produce new discoveries. So together, These telescopes give us a complete view of the universe across the entire electromagnetic spectrum. We can see cool objects through infrared. We can see normal objects through visible light. We can see hot objects through ultraviolet and X-rays. We can study the most energetic and violent objects through gamma rays. This multi-wavelength approach has been revolutionary. It's revealed that the universe is far richer and more complex than we ever imagined. Every object looks different when observed in different wavelengths. We see different features, different properties. By combining observations from many telescopes, we get a complete picture. Let me talk in detail about some of the major discoveries that space telescopes have made, because understanding what we've learned helps you appreciate the power of these instruments. First, there's the question of how many galaxies exist. Before the 20th century, astronomers thought the universe might consist only of the Milky Way galaxy. They didn't know that other galaxies existed beyond our own. Then, in the 1920s, astronomers discovered that there were other galaxies. The universe was much larger than anyone had thought. But how many galaxies? The Hubble helped answer this question. The galaxy survey done by Hubble suggested there were maybe 50 to 100 billion galaxies. Later estimates based on more observations suggested perhaps 200 billion galaxies. But then the JWST observed galaxies so distant and so numerous that estimates have been revised upward again. There might be 2 trillion galaxies or more. The universe is far richer in galaxies than we ever imagined. When you think about it, this is staggering. 2 trillion galaxies. If each galaxy has on average 100 billion stars, that's 200 billion stars. Written out, that's 200 quintillion stars. The scale is incomprehensible. And if even a tiny fraction of those stars have planets, and an even tinier fraction of those planets have life, there could be vast numbers of living worlds out there. This is why the search for life on exoplanets is so important. It's not just a curious side project. It's an attempt to answer the fundamental question, are we alone in the universe? I want to share a personal moment before we talk about discoveries. When I first saw the Hubble Deep Field image as a child, I was struck by something profound. It was this tiny picture, a region of sky about the size of a grain of sand held at arm's length, filled with thousands of galaxies. Each point of light was an entire galaxy with billions of stars. And the Hubble had shown that if you looked at any random piece of sky, you'd see thousands of galaxies. I remember thinking the universe is so much bigger than I imagined, and we're so small. That image changed how I thought about the cosmos. It made me want to understand it. It made me realize that there was so much to learn. Now let me talk about one of the most important discoveries. One of the most important discoveries is the expansion of the universe. Before the 20th century, astronomers thought the universe was static, unchanging. But in the 1920s, Edwin Hubble, after whom the Space Telescope is named, discovered that the universe is expanding. Distant galaxies are moving away from us. The farther away they are, the faster they're moving. This was a revolutionary discovery. It meant the universe had a beginning, the Big Bang. It meant the universe is evolving. It meant everything we see around us is part of a dynamic, expanding cosmos. In the 1990s, the Hubble Space Telescope made an observation that would have profound implications. Astronomers used Hubble to measure the expansion rate of the universe more precisely. They observed distant supernovae and measured how far away they were. They compared the expansion rate at different distances, at different times. And they found something shocking. The expansion of the universe isn't slowing down. It's speeding up. Something is pushing galaxies apart faster and faster. Astronomers called this unknown force dark energy. This discovery was so significant that it won the 2011 Nobel Prize in Physics, and it came from Hubble observations. The Hubble didn't discover dark energy directly, but it provided the key evidence. It revealed that the universe's expansion is accelerating, which led to the hypothesis of dark energy. Another major discovery came from a remarkable set of observations called the deep field images. In December 1995, astronomers made a proposal to the Hubble Space Telescope Time Allocation Committee. The proposal was considered radical by many. They wanted to observe a tiny region of sky, an area about the size of a grain of sand held at arm's length. This region appeared to be completely empty. There was nothing there, or so it seemed. Many astronomers thought this was a waste of observing time. The Hubble's time is precious and limited. Why spend it on an empty patch of sky when there were so many interesting objects to observe? But the proposers believed that this empty patch of sky would surprise them. They believed that if they looked deep enough, if they gathered enough light, they would see something unexpected. They were right. When the images came back from the Hubble, they showed not empty space, but thousands of galaxies. The tiny region of sky, barely 5 square arc minutes, contained nearly 3,000 galaxies. Each of those tiny points of light was an entire galaxy containing billions of stars. The implications were staggering. If this small patch of sky, which represented just one part of the universe, contained thousands of galaxies, then scaling up, the entire sky must contain billions or trillions of galaxies. The universe was vastly more populated with galaxies than anyone had realized. The deep field images became iconic. They've been seen by millions of people. They've inspired generations of astronomers. Every scientist interested in astronomy has seen the deep field image at some point. It's become a symbol of what Hubble can do: reveal hidden universes in the sky. Following the success of the deep field, Hubble conducted other deep field observations. The Hubble Ultra Deep Field, observed in 2004, looked at an even smaller region, just 11 square arc minutes, and found over 10,000 galaxies. The Hubble Extreme Deep Field, observed in 2012, pushed even deeper and found galaxies at the edge of the observable universe, from when the universe was only a few 100 million years old. Each of these observations pushed our understanding further. They showed us a universe far richer than we had imagined. Now, with the JWST, we're seeing even deeper. The JWST's first deep field image, released in 2022, shows galaxies from when the universe was only a few 100 million years old. We're seeing the early universe as it was billions of years ago. What these observations revealed is a universe that is far older, far larger, and far more complex than we would have guessed just by looking at our own galaxy or the nearest galaxies. We're not at the center of anything special. We're not in a unique location. We're in a typical region of a vast ancient cosmos filled with countless galaxies. This is philosophically profound. It's a continuation of a trend that started with Copernicus. First, Copernicus showed that Earth is not at the center of the solar system. Then we learned that our sun is not special. It's a typical star among billions in the Milky Way. Then we learned that the Milky Way is not special. It's a typical galaxy among billions in the universe. With each realization, we become more humble. We've realized our place in the cosmos is not particularly central or special. We're inhabitants of one planet, orbiting one star, in one galaxy, among billions of galaxies, in an ancient and vast universe. But there's another side to this. While we're not physically central or special, there's something remarkable about our existence. We have developed consciousness. We have developed intelligence. We have learned to ask questions about the universe. We have built these incredible machines, space telescopes, to observe the cosmos and understand it. That's special. That's remarkable. The ability to observe the universe, to collect ancient light that's been traveling for billions of years, to analyze that light and extract scientific understanding. That's a profound achievement. It shows the power of human curiosity and ingenuity. It shows what we can accomplish when we work together toward a common goal. Another major discovery came from the deep field observations. In 1995, the Hubble observed a tiny piece of sky, an area about the size of a grain of sand held at arm's length. This was considered a waste of observing time by many people. Surely there was nothing there. It was just empty sky. But when the images came back, astronomers were amazed. The deep field image showed not empty space, but thousands of galaxies. Each one of those tiny points of light was an entire galaxy containing billions of stars. It showed that the universe is far more densely populated with galaxies than anyone had imagined. This observation was profound philosophically. It suggested that if you picked any random piece of sky, any direction you looked, you would see thousands of galaxies. The universe is essentially infinite in extent and contains innumerable galaxies. The Hubble also provided evidence for supermassive black holes at the centers of galaxies, one of the most fascinating discoveries. By observing stars orbiting near the center of our galaxy, the Milky Way, astronomers could infer the presence of a massive object, millions of times the mass of the Sun, that must be a black hole. Similar evidence was found in many other galaxies. This led to the realization that virtually every large galaxy has a supermassive black hole at its center. Black holes are objects so dense that not even light can escape them. They have an event horizon, a boundary beyond which nothing can escape. They're predicted by Einstein's general relativity, but for decades, astronomers weren't sure if they actually existed in nature. The evidence for black holes came from observing stars and gas orbiting around an invisible massive object. By measuring how fast these objects orbit and how far away they are, astronomers can calculate the mass of the central object. If the mass is very large and concentrated in a small region, it must be a black hole. Hubble observations of the center of the Milky Way provided compelling evidence. Stars are observed orbiting rapidly around an invisible object at the galactic center. By tracking their orbits for decades, astronomers calculated that the central object has a mass of about 4 million times the Sun's mass, compressed into a region smaller than our solar system. This must be a black hole. We call it Sagittarius A star. But here's the remarkable discovery. Virtually every large galaxy has a supermassive black hole at its center. Black holes with masses ranging from millions to billions of times the Sun's mass exist at the hearts of galaxies. This was surprising because it suggested that the formation and evolution of galaxies are intimately connected to black holes. Early in a galaxy's life, gas falling into the central black hole releases enormous energy, heating the galaxy and regulating star formation. Understanding this connection was a major insight from space telescope observations. The Chandra X-ray Observatory has made remarkable discoveries about black holes and neutron stars. It has observed the radiation from matter spiraling into black holes, measured their properties, and studied how they interact with their surroundings. Neutron stars are the remnants of massive star explosions. Incredibly dense objects where a teaspoon of material would weigh 1 billion tons. Chandra observations have revealed the properties of neutron stars in unprecedented detail. The Chandra X-ray Observatory made discoveries about the hot gas in galaxy clusters. Galaxy clusters are the largest structures in the universe. They contain hundreds or thousands of galaxies held together by gravity. Chandra observed X-rays from the hot gas between galaxies in these clusters. It revealed that the gas is incredibly hot, millions of degrees. It also revealed something surprising. There's far more mass in the hot gas than in all the stars in all the galaxies combined. Most of the matter in galaxy clusters is in this hot gas, not in the galaxies themselves. Chandra also made discoveries about black holes and neutron stars. It observed the jets of material being expelled by supermassive black holes at tremendous speeds. It observed the radiation from material spiraling into black holes. It studied neutron stars, some of the most extreme objects in the universe, with densities so high that a teaspoon of neutron star material would weigh 1 billion tons. The Spitzer Space Telescope revealed that star formation happens much more efficiently than expected. It observed star-forming regions in great detail, showing how stars are born from clouds of gas and dust. It found that planets are far more common around other stars than anyone had anticipated. Essentially, every star has planets. This was revolutionary because just decades earlier, we didn't know if planets existed around other stars. Spitzer provided evidence for potentially habitable planets by observing exoplanet atmospheres and measuring their properties. It identified planets in the habitable zone, the region around a star where liquid water could exist. This discovery was profound because it suggested that there might be many potentially habitable worlds out there. One particularly interesting discovery involved planets around very old stars. Spitzer found evidence for planets around white dwarfs, the remnants of dead stars. These planets had somehow survived the star's death, suggesting that planetary systems can be robust enough to survive stellar catastrophes. Another fascinating discovery: planets are surprisingly common around nearby stars. Proxima Centauri, the closest star to our Sun at 4.2 light-years away, has planets. One of them, Proxima b, is in the habitable zone, meaning liquid water might exist there. With future space telescopes, we might be able to directly observe this planet and analyze its atmosphere for signs of life. Now let me talk more deeply about costs, because when you're spending billions of dollars on space telescopes, it's worth understanding where that money goes and whether it's justified. Building a space telescope is one of the most expensive and complex engineering projects humans undertake. Let me break down the costs. First, there's the optical system. For the Hubble, the primary mirror is 2.4 meters in diameter. It's made of Pyrex glass that was ground and polished to an incredibly precise shape. The tolerance is so tight that if the mirror were the size of Earth, the largest bump on its surface would be about the size of a car. Getting that kind of precision requires specialized manufacturing techniques and equipment. For the James Webb Space Telescope, the primary mirror is larger, 6.5 meters in diameter, but it's not a single piece. It's made up of 18 individual hexagonal segments. Each segment is made of beryllium coated with gold. Beryllium is an expensive material because it has unique properties. It's lightweight, it doesn't expand much when temperatures change, and it can be polished to extreme precision. But beryllium is toxic and difficult to work with, which adds to the cost. The mirror segments and their supporting structure cost roughly $300 to $400 million. The mirror alone accounts for a significant fraction of the JWST's total budget. Then there are the instruments. A space telescope needs multiple instruments to do different types of observations. The Hubble carries cameras, spectrographs, and other instruments. The JWST carries even more sophisticated instruments because it's observing infrared light. One of the JWST's instruments is the near-infrared camera, which contains an infrared detector with over 4 million individual pixels. Each pixel has to be perfectly calibrated. The instruments have to operate reliably in the vacuum of space for years or decades without maintenance. They have to be protected from radiation that would damage or degrade electronics. They have to survive extreme temperatures. The scientific instruments on the JWST cost over $1.5 billion to develop and build. Then there's the spacecraft bus, the main structure that holds all the components together. The bus contains power systems, thermal control systems, propulsion systems, communication systems, data handling systems. The JWST's spacecraft bus, including its famous sunshield, represents hundreds of millions of dollars of cost. The sunshield is particularly interesting because it's so complex and expensive. The JWST observes infrared light, which means its instruments need to be incredibly cold, about 40 Kelvin or minus 233 degrees Celsius. If the sun's heat reaches the telescope, it will warm up the instruments and ruin the observations. So the JWST has a 5-layer sunshield that's about 21 by 14 meters, roughly the size of a tennis court. Each layer is made of specialized materials that reflect heat. The sunshield alone cost hundreds of millions of dollars to develop and build. The launch vehicle is another massive expense. The JWST launched on a European Ariane 5 rocket. Each Ariane 5 launch costs about $500 million. For comparison, the Hubble launched on the Space Shuttle, which cost about $450 million per mission in the 1990s. Getting your telescope into space is one of the single largest costs in the entire project. Then there are all the people. Designing, developing, building, and launching a space telescope requires a huge workforce. The Hubble project employed over 5,000 people during its development. The JWST employed even more. You're paying salaries for engineers, scientists, technicians, project managers, administrators, quality assurance specialists. Over many years, these salaries add up to hundreds of millions or even billions of dollars. You need testing facilities, clean rooms where components can be assembled and tested without contamination. You need thermal vacuum chambers to test how instruments behave in the environment of space. You need optical benches to test how the optical systems work. You need specialized equipment that costs millions of dollars. You need ground stations on Earth to communicate with a telescope. These are expensive facilities with large antennas and sophisticated electronics. For the JWST, NASA uses facilities in several countries to maintain communication with the telescope. You need supercomputers to process the data from the telescope. A single observation from the JWST can generate hundreds of gigabytes of data. You need powerful computers to store, process, and analyze all this data. You need teams of software engineers to write the programs. You need archival systems to store data for decades. Scientists all over the world download and use data from Hubble and other space telescopes. NASA has to maintain vast data archives. You need staff to maintain and troubleshoot problems. Both Hubble and JWST have teams of people available 24/7 to monitor operations and respond to problems. So the total cost of a major space telescope is truly enormous. Here's a breakdown of some of the major ones. The Hubble Space Telescope. The development and construction cost about $2.5 billion in 1990s dollars. In today's dollars, accounting for inflation, that's roughly equivalent to $5 to $6 billion. This includes all the design, engineering, construction, launch, and the first several years of operations. Since then, the costs of servicing missions and continued operations add more. Over its entire 30-plus year operational life, the total cost has been maybe $10 to $15 billion when you include all operations and maintenance. The James Webb Space Telescope. The total cost reached about $10 billion. This is the highest price tag for any scientific instrument ever built. During development, costs kept escalating. The original estimate was $500 million. By the mid-2000s, estimates were around $2 billion. By 2010, it was $6 to $7 billion. By launch in 2021, it had reached $10 billion. The cost overruns were controversial and led to criticism of the project. The Chandra X-ray Observatory, about $1.5 billion in total development and operations costs. The Spitzer Space Telescope, about $800 million in development and operations costs. The TESS exoplanet mission, about $600 million. Future space telescopes being planned will cost billions more. The Nancy Grace Roman Space Telescope is estimated to cost about $2 to $3 billion. Other concepts for future telescopes could cost $5 to $10 billion or more. Now you might ask, is it worth it? Is spending $10 billion on a single telescope justified? This is a legitimate question. A person could reasonably argue that $10 billion could be spent on education, on medical research, on poverty reduction, on climate change, on infrastructure, on mental health services. These are all important causes. Every dollar spent on space telescopes is a dollar not spent on something else. But consider what we get for that money. The Hubble revolutionized astronomy. It fundamentally changed our understanding of the universe. Every school child has seen a Hubble image. The discoveries it made have inspired millions of people to pursue careers in science. The Hubble images of nebulae, galaxies, and star clusters are among the most beautiful scientific images ever created. More importantly, the Hubble provided evidence that the universe's expansion is accelerating, which led to the discovery of dark energy. This discovery was so significant that it won the 2011 Nobel Prize in Physics. Without the Hubble, we wouldn't have discovered dark energy, one of the most profound mysteries in physics. The JWST is already making breakthrough discoveries. It's observing galaxies so distant that their light has been traveling for over 13 billion years. It's directly imaging planets around other stars. It's characterizing the atmospheres of exoplanets, searching for biomarkers, evidence of life. These are fundamental questions about the universe and our place in it. Moreover, the money spent on space telescopes goes back into the economy. It pays salaries for thousands of engineers and scientists. It supports manufacturing facilities and high-tech companies. It drives innovation in optics, materials science, electronics, data processing. Many technologies we use today were developed for space telescopes and the space program. Precision manufacturing techniques, advanced materials, radiation-hardened electronics, data compression algorithms, thermal insulation technologies, optical coatings. These technologies have applications in medicine, communication, energy production, transportation. For instance, the technology for detecting breast cancer through thermography was developed from infrared detector technology created for space telescopes. The technology for water purification systems was developed for spacecraft. Cordless tools were invented for the space program. GPS was developed for military purposes but is used everywhere now. The internet itself grew out of ARPANET, which was partly motivated by space program needs. So the return on investment, both in terms of knowledge gained and technological spin-offs, is substantial. Furthermore, in the context of national spending, the investment in space telescopes is quite small. The United States federal budget is roughly $6 trillion per year. NASA's budget is about $25 billion per year. Space telescopes might account for $1 to $2 billion of that. So space telescopes represent about 0.03% of the federal budget. As a percentage of GDP, it's even smaller. For a wealthy nation, spending 0.03% of the budget on understanding the universe is quite reasonable. It's an investment in knowledge, in inspiration, in pushing the boundaries of human capability. When you think about it in these terms, as a tiny percentage of national spending that yields enormous scientific and inspirational returns, the investment in space telescopes becomes clearly justified. And now the James Webb Space Telescope is making its own remarkable discoveries. It's observing galaxies so distant that their light has been traveling for over 13 billion years. These are galaxies from when the universe was very young, only a few 100 million years old. By studying these distant galaxies, astronomers can understand how galaxies formed and evolved. The JWST has already surprised astronomers. It's finding that galaxies formed faster and earlier than we thought. Galaxies that shouldn't have had time to grow so large have been observed at great distances. This suggests that our understanding of galaxy formation might need to be revised. The JWST has also observed the atmosphere of a distant exoplanet, a planet around another star. It detected water, methane, and other molecules in the atmosphere. This is the first direct detection of atmospheric molecules in an exoplanet. It's a step toward finding biosignatures, evidence of life, around other stars. The JWST is also studying star-forming regions. It's seeing through dust clouds to observe newborn stars. It's watching how planets are forming around young stars. It's providing unprecedented detail about how stars and planetary systems are born. These discoveries, made possible by space telescopes, have transformed our understanding of the cosmos. We now know that the universe is vastly larger than we thought, far older than we thought, and far more complex than we thought. We know that galaxies are common, that planets are common, that black holes are common. We know that the universe is expanding faster and faster due to dark energy. We're beginning to understand how galaxies formed, how stars are born, whether life might exist around other stars. All of this knowledge comes from space telescopes. From machines orbiting in space, collecting light that's been traveling through the vacuum for millions, billions of years, and sending that light back to us so we can study it and understand the universe. Let me talk about the future. There are many exciting space telescope projects in development. The Nancy Grace Roman Space Telescope, formerly called the Wide Field Infrared Survey Telescope, is scheduled to launch in the mid-2020s. It's named after Nancy Grace Roman, a pioneering astronomer who was instrumental in planning the Hubble Space Telescope. The Roman telescope will observe infrared light and has a very wide field of view, much wider than the JWST. This will allow it to survey large areas of sky and find rare objects. It will be particularly useful for searching for exoplanets and studying dark matter. Roman will use gravitational microlensing to detect exoplanets, observing how stars' light is bent by the gravity of planets orbiting them. This technique is good at finding planets at large distances from their stars, planets that other methods might miss. The Vera C. Rubin Observatory, actually a ground-based telescope, not a space telescope, but worth mentioning, is being built in Chile and will survey the entire night sky repeatedly. It will detect transient phenomena, things that change over time. It will find asteroids, supernovae, variable stars, black holes. By repeatedly imaging the sky, Rubin will create a movie of the universe, showing how things change day by day, month by month. There are concepts for future large space telescopes that are even more ambitious than the JWST. The Habitable Exoplanet Observatory, HabEx, is being studied by NASA. It would be about 4 to 6 meters in diameter, larger than Hubble, but smaller than JWST. It would be specifically designed to image and characterize Earth-sized exoplanets. It could potentially detect oxygen and other biosignatures in exoplanet atmospheres. The Large UV/Optical/IR Telescope, LUVOIR, is another concept. It would be even larger, up to 15 meters in diameter. It would observe ultraviolet, visible, and infrared light. It would be thousands of times more sensitive than the human eye. It could potentially resolve the surfaces of nearby stars and image exoplanets directly. Other concepts involve multiple mirrors operating in coordination, forming a virtual telescope. Imagine having multiple space telescopes in different orbits, working together. The data from each would be combined to create images with resolution far better than any single telescope could achieve. This is similar to interferometry techniques used in radio astronomy. On July 12, 2022, NASA released 4 images taken by the James Webb Space Telescope. Scientists had spent months preparing for this moment. They'd picked out some of the most iconic objects in astronomy: a classic galaxy cluster, a star-forming nebula, a distant galaxy with its light bent by gravitational lensing, and the atmosphere of an exoplanet. These weren't meant to be the most scientifically important observations. They were meant to show the world what this machine could do. When the images appeared on screens around the globe, people wept. Astronomers wept. The public wept. Scientists who had worked on the project for decades saw their life's work vindicated. And people who knew nothing about astronomy looked at these images and felt something profound: awe at the universe revealed with clarity that had never been possible before. Those images changed what was possible in astronomy. They showed a universe more detailed, more ancient, more complex than we'd ever seen. And we were only at the beginning. The James Webb Space Telescope isn't just another space telescope. It's fundamentally different from Hubble. It observes infrared light instead of visible light. It's much larger. It's more powerful. It can see deeper into space and further back in time. And it's been making discoveries so profound that they're forcing astronomers to rewrite how we understand the universe. But the story of how we got here, to this moment where we can look at light that's been traveling for over 13 billion years and extract meaning from it, is itself incredible. It's a story of ambition and failure, of cost overruns and technical challenges, of people working together across decades to build something that seemed impossible. And it's a story that isn't over. The James Webb is still just getting started. The first thing you need to understand about the James Webb Space Telescope is why it exists. Why did we need something bigger and more powerful than Hubble? Hubble is an incredible telescope. It revolutionized astronomy. It showed us the universe in unprecedented clarity. But it observes primarily in visible light and ultraviolet light. These are wavelengths that our eyes can see, or wavelengths very close to what our eyes can see. The problem is that the most distant galaxies are so far away that their light has been traveling for billions of years to reach us. As that light travels through the expanding universe, the wavelengths get stretched, a phenomenon called redshift. Light that left a distant galaxy as visible light gets stretched into infrared wavelengths by the time it reaches Earth. So if you want to observe the most distant galaxies, you need to observe infrared light. Hubble can observe some infrared, but it's limited. The James Webb is designed specifically to observe infrared light. That's its strength. That's what makes it revolutionary. But designing a telescope to observe infrared light isn't straightforward. Infrared is heat radiation. Everything warm emits infrared. The sun emits infrared. The Earth emits infrared. Even the telescope itself, if it's warm, will emit infrared radiation that will overwhelm the faint infrared signals from distant galaxies. So the James Webb has to be incredibly cold. Its infrared instruments need to operate at a temperature of about 40 Kelvin, that's minus 233 degrees Celsius, colder than anywhere naturally occurring in the solar system. To achieve this temperature, the telescope has a sun shield about the size of a tennis court, 21 by 14 meters. This shield protects the telescope from the heat of the sun and allows it to radiate heat away into space. The mirror itself is 6.5 meters in diameter, made up of 18 hexagonal segments made of beryllium coated with gold. Gold was chosen because it reflects infrared light efficiently and won't degrade over time. The segments can be individually adjusted to align perfectly, creating a mirror that functions as one large, seamless reflector. The James Webb took decades to develop. The concept started in the mid-1990s. Engineers and scientists envisioned a telescope that would be larger than Hubble, more powerful, capable of observing the earliest galaxies in the universe. But the technical challenges were immense. The complexity was staggering. The original cost estimates were maybe $500 million. By 2010, estimates were around $6 billion. By 2018, when costs were spiraling out of control, Congress set a cap of $8 billion. By the time the telescope launched in December 2021, the total cost had reached about $10 billion, making it the most expensive scientific instrument ever built. The delays were legendary. The telescope was originally supposed to launch in 2007. Then it was pushed back to 2011, then 2018. Technical problems kept arising. Component manufacturers fell behind. Designs had to be revised. The project faced criticism from Congress, from the public, from scientists who wondered if the money could be better spent. But supporters of the project argued that this was necessary, that this telescope would answer fundamental questions about the universe. That understanding the early universe, understanding how galaxies formed, understanding whether life exists around other stars. These were questions worth investing in. And eventually, on December 25th, 2021, Christmas Day, the James Webb Space Telescope launched on a European Ariane 5 rocket. The launch itself was anticlimactic in some ways. A flawless liftoff. The rocket performed perfectly. But what came next was terrifying for everyone involved. Unlike Hubble, which orbits Earth at an altitude of about 600 kilometers and can be serviced by astronauts, the James Webb is located at Lagrange Point 2, a point about 1.5 million kilometers from Earth, where the sun's gravity and Earth's gravity balance. It's too far away for any spacecraft to reach and repair. If anything went seriously wrong during deployment, the mission would be lost, and the James Webb had to deploy. It couldn't fit into the rocket fully assembled. It had to fold up, origami style, to fit inside the rocket payload. Once in space, it had to unfold. The sun shield had to deploy. The mirror segments had to unfold. The instruments had to power on and calibrate. Each step was a potential point of catastrophic failure. Over the next month, as the telescope cruised toward Lagrange Point 2, mission control teams in Baltimore watched nervously as each deployment step was executed. The sun shield deployed successfully. The mirror segments unfolded. The instruments powered on. Each success was met with cheers. But people knew that one major failure could end everything. The deployment was completed successfully. Then came the most anxiety-inducing part: calibration and focus. The mirror segments had to be aligned perfectly to within a fraction of a micron. If the alignment was off, the images would be blurry. The instruments had to be tested and calibrated. The telescope had to be brought into focus. This took months. Scientists monitored every step. Engineers analyzed every piece of telemetry. And gradually the universe came into focus. When the first images were released in July 2022, they were stunning. The image of the galaxy cluster showed thousands of galaxies in fine detail. Galaxies that appeared as tiny smudges to Hubble appeared with structure and detail in the JWST image. The image of the Carina Nebula, a star-forming region, showed newborn stars embedded in clouds of gas and dust with clarity that had never been seen before. The image of the Southern Ring Nebula showed a dying star with its expelled shells of gas. The spectrum of an exoplanet's atmosphere showed the chemical composition: water, methane, other molecules. These images did more than impress people. They revealed something unexpected. The galaxies were larger and more developed than they should be. According to our models of galaxy formation, galaxies in the early universe should be small and chaotic. But the JWST was seeing galaxies that were surprisingly large and organized, existing when the universe was only a few 100 million years old. This discovery forced astronomers to reconsider their models. Either our understanding of galaxy formation is incomplete, or something different happened in the early universe. The question of why galaxies formed so quickly and grew so large so fast is now a major area of research driven by JWST observations. Since those first images, the James Webb has continued to make discoveries. It's observed the most distant galaxy ever seen, so far away that its light has been traveling for over 13.5 billion years. It studied star-forming regions, revealing the process by which stars and planets are born. It's observed the atmospheres of exoplanets, detecting water, methane, carbon dioxide, and other molecules. It's studied supernovae remnants. It's observed gravitationally lensed galaxies. It's observed black holes. Every observation has revealed something new. Every image has sparked new questions. But what exactly can the James Webb do? How does it work? What are its capabilities? The fundamental capability is infrared observation. The James Webb observes wavelengths from about 0.6 micrometers to 28 micrometers. This spans from the visible spectrum into the near-infrared, mid-infrared, and some far-infrared wavelengths. Hubble observes primarily visible light from about 0.1 to 1 micrometer. So the JWST observes wavelengths that are much longer than Hubble's primary range. Longer wavelengths mean the telescope can see objects that are cool rather than hot. It can see through dust clouds that block visible light. It can see red-shifted light from distant galaxies. light that started as visible light but has been stretched into infrared by the expansion of the universe. The mirror collects infrared light and focuses it. The light is then directed to different instruments depending on what kind of observation you want to make. There's the near-infrared camera, which observes near-infrared wavelengths from about 0.6 to 5 micrometers. This is the closest to visible light. It can take images of galaxies, nebulae, and stars. It can observe the light from distant galaxies and measure their properties. It has a detector with over 4 million pixels, so it can create detailed images. There's the near-infrared spectrograph, which splits infrared light into its component wavelengths, allowing astronomers to determine the chemical composition and physical properties of objects. If you want to know what an exoplanet's atmosphere contains, you use the spectrograph. It spreads the light from the object across a detector, creating a spectrum, a rainbow of light at different wavelengths with bright lines and dark lines corresponding to different elements and molecules. There's the mid-infrared instrument, which observes longer wavelength infrared light from about 4 to 28 micrometers. This allows observation of cooler objects and objects that are hidden behind dust. There's the fine guidance sensor, which helps point the telescope and keep it stable. All of these instruments are incredibly sensitive. They can detect individual photons. They have to be because the objects being observed are extremely distant and faint. The sensitivity comes from the detectors, specialized devices that convert photons into electrical signals. But detecting individual photons requires extremely low noise. Thermal noise from atoms moving around at room temperature would overwhelm the signal. So the detectors are cooled to extremely low temperatures, about 40 Kelvin for some of them. The sun shield makes this possible. 5 layers of material, each designed to reflect heat and radiate it away, keep the telescope cold enough despite being in the intense heat of the sun-facing side of space. This combination of a large mirror, infrared capability, extreme sensitivity, and sophisticated instruments makes the James Webb more powerful than any telescope that's come before. But power isn't just about size, it's about what you can actually do with that power. Let me talk about some specific capabilities and what they mean. One major capability is distance measurement. Astronomers can measure how far away distant galaxies are by analyzing the light they receive. The redshift of the light tells you how much the universe has expanded since that light left the galaxy. From redshift, you can calculate distance and therefore how long ago the light left the galaxy. The JWST can measure redshifts for galaxies that are so distant and faint that Hubble couldn't observe them at all. This allows astronomers to study galaxies in the early universe just a few 100 million years after the Big Bang. Another capability is chemical analysis. By taking spectra of objects, the JWST can determine what chemical elements and molecules are present. For exoplanet atmospheres, this is revolutionary. Astronomers can detect water, methane, carbon dioxide, and other molecules. Over time, with multiple observations, they can build up a picture of what the atmosphere contains. The goal eventually is to detect biosignatures, chemical evidence of life. Another capability is imaging through dust. Dust obscures visible light, which is why Hubble struggles to observe star-forming regions. The stars are hidden inside dust clouds. But infrared light penetrates dust much better. The JWST can see through dust clouds to observe stars being born, watching the process of stellar birth in detail. Another capability is detecting faint objects. The JWST's sensitivity means it can detect objects that are millions of times fainter than what Hubble can see. This opens up the possibility of observing the most distant and ancient objects in the universe. Another capability is high angular resolution. The JWST's mirror is large enough that it can resolve fine detail in distant objects. It can see the structure of galaxies billions of light years away. It can see the shapes of nebulae. It can resolve individual stars in crowded star fields. All of these capabilities combined make the JWST a revolutionary instrument. Let me talk more specifically about what it's discovered, because over the past few years since launch, it's made discoveries that are changing astronomy. The most famous discovery is the observation of galaxies in the early universe. Before the JWST, the most distant galaxies known were from when the universe was about 400 to 500 million years old. The JWST has observed galaxies from when the universe was only 200 to 300 million years old. These are extremely early galaxies observed when the universe was in its infancy. But here's the surprise. These early galaxies are large. They contain hundreds of billions of stars. They're structured. They're not the small, chaotic, disorganized things that models predicted. The discovery that galaxies formed so early and grew so large so fast has forced astronomers to reconsider how galaxy formation works. This is a profound discovery because it means our models of galaxy formation are incomplete or wrong. We thought we understood the early universe. We thought we knew how structures formed. But the JWST is showing us that reality is more complex than we thought. Another major discovery is the observation of star-forming regions. The JWST has looked at nearby star-forming nebulae and revealed the details of how stars are born. It can see young stars embedded in dust clouds. It can see the disks of material around young stars where planets are forming. It can observe the jets of material being expelled by young stars. These observations are teaching us about planetary formation at a level of detail that wasn't possible before. Another discovery is the observation of exoplanet atmospheres. When a planet transits in front of its star, some of the star's light passes through the planet's atmosphere. Different elements and molecules absorb light at different wavelengths, creating a spectrum. The JWST can measure these spectra in detail, revealing the composition of exoplanet atmospheres. It's detected water, methane, carbon dioxide, and other molecules. One particularly interesting observation was the atmosphere of K2-18b, a super-Earth or mini-Neptune about 120 light-years away. The JWST detected water vapor and other molecules in its atmosphere. K2-18b is in the habitable zone of its star, meaning liquid water could exist on its surface. The detection of water and other molecules in its atmosphere was exciting because it showed that the JWST can analyze the atmospheres of potentially habitable planets. Another discovery involves gravitationally lensed galaxies. When light from a distant galaxy passes near a massive object like another galaxy or galaxy cluster, the gravity bends the light, magnifying it. This is called gravitational lensing. The JWST has observed several gravitationally lensed galaxies, and because the light is magnified, it can see fine details that would otherwise be impossible to resolve. It's like nature provides us with a magnifying lens, and the JWST can take advantage of that to see deeper into the early universe. Another discovery is about black holes. The JWST has observed light from materials spiraling into supermassive black holes. It's observed the jets of material being ejected by black holes at nearly the speed of light. It's studying how black holes grow and how they affect their surrounding galaxies. But perhaps most importantly, the JWST is making discoveries that nobody predicted. It's finding things that surprise astronomers, things that don't fit existing models. That's the sign of a truly revolutionary telescope. It's not just confirming what we already thought, it's revealing aspects of the universe that we didn't know to look for. The JWST is still operating. It's been in space for about 4 years now. Astronomers estimate that it can continue operating for another decade or more, depending on how much fuel remains for station keeping. There's enough consumables, liquid helium for cooling, propellant for orbital adjustments, to keep it operating until at least 2030 or beyond. And there are so many more observations planned. There are so many more discoveries waiting to be made. Let me talk about what's coming next. What observations are planned? What questions is the JWST trying to answer? One major area of focus is understanding the early universe. Astronomers want to observe even more distant galaxies, pushing back further in time. They want to understand how the first galaxies formed, how they evolved, how structures grew from the tiny density fluctuations in the early universe to the galaxies and galaxy clusters we see today. Another major area is exoplanet atmospheres. Astronomers want to continue observing and analyzing the atmospheres of planets around other stars. Eventually, the goal is to find biosignatures, evidence of life. Oxygen is a biosignature. Methane can be a biosignature in certain combinations. If we detect oxygen and methane together in an exoplanet atmosphere, combined with water and carbon dioxide, that could indicate life. Another major area is star formation. Astronomers want to observe star-forming regions in detail, understand how stars form, understand how planetary systems form around young stars. This is fundamental to understanding our own origins. Another major area is black holes. Astronomers want to study the growth of supermassive black holes, understand how they form, understand how they affect galaxy evolution. Another major area is the most distant supernova. When massive stars explode as supernova, they can briefly become as bright as an entire galaxy. The JWST can observe these events at great distances, revealing the properties of the early universe. Another major area is searching for signs of life. While the primary mission is observing the early universe and studying stars and galaxies, the ultimate goal is to answer the question, are we alone? If life exists around another star, the JWST might be able to detect evidence of it by observing atmospheric biomarkers. But there are also longer-term visions for what's possible. Astronomers are already thinking about what comes after the James Webb. What will be the next revolutionary telescope? One concept is called LUVOIR, the Large UV/optical/IR telescope. It would be even larger than JWST, with a mirror up to 15 meters in diameter. It would observe ultraviolet, visible, and infrared light. It would be thousands of times more sensitive than the human eye. It could potentially resolve details in nearby exoplanets, perhaps even see signs of continents or oceans. Another concept is called HabEx, the Habitable Exoplanet Observatory. It would be specifically designed to image Earth-like exoplanets and analyze their atmospheres for biosignatures. The technological challenges are immense. You'd be trying to photograph a planet that's 1 billion times fainter than its star. But it might be possible with advanced optics and clever techniques like star shades. There are also concepts for telescopes on the moon or elsewhere in the solar system. Lunar observatories wouldn't have Earth's atmosphere to deal with. They could be far larger than current space telescopes. A telescope on the far side of the moon would be shielded from Earth's radio noise, making it ideal for certain observations. But all of this is future. Right now, the James Webb is doing work that's revolutionary, that's changing our understanding of the universe right now, in the present. I think about what we've learned from the James Webb in just its first few years of operation. We've seen galaxies earlier than we thought possible. We've challenged our understanding of galaxy formation. We've detected the atmospheres of exoplanets. We've revealed star-forming regions with unprecedented detail. We've observed black holes and supernovae and gravitationally lensed galaxies. And it's just the beginning. The JWST has been allocated observation time through at least 2030. There are thousands of observation proposals from astronomers around the world competing for limited observing time. Everyone wants to use this incredible telescope. Everyone has questions they want to answer. The process for getting time on the JWST is competitive. Astronomers submit proposals explaining what they want to observe and why it's scientifically important. A panel of experts reviews the proposals and ranks them by scientific merit. The most promising and important observations get selected. It's a rigorous process, which is how it should be. You want the best science coming out of such an expensive instrument. And the science that's coming out is genuinely exciting. Every few weeks, new papers are published based on JWST observations. Every observation reveals something new, answers some questions, and raises others. One of the beautiful things about the James Webb is that it's accessible to the entire world. The data it collects is made available to all astronomers, not just NASA scientists. After an initial period where the astronomers who propose the observation have exclusive access, the data becomes public. Anyone with access to a computer can download JWST data and analyze it. Scientists all over the world are making discoveries from this shared resource. This is how science should work. We invest in this incredible instrument, we collect data, we share it, and we allow the global scientific community to benefit from it. Discoveries are made that advance human knowledge. But there's something else profound about the James Webb. It's a symbol. It's a symbol of human ambition, of our willingness to tackle incredibly difficult technical challenges, of our commitment to understanding the universe. Building the James Webb took decades. Thousands of people worked on it. Engineers at hundreds of companies and institutions, scientists planning observations, technicians assembling components, programmers writing software, project managers coordinating everything. It was a massive human effort, and it was expensive. $10 billion. You could spend a lot of other ways. You could build hospitals, schools, roads, bridges. You could reduce poverty, fight disease, address climate change. But the James Webb represents a choice that a society makes, a choice to invest in understanding, a choice to look outward and ask fundamental questions about the universe, a choice to believe that knowing things, understanding things, is valuable for its own sake. This is worth celebrating. This is worth supporting. This is what makes humanity remarkable, not just our capacity to build things, but our desire to understand. When I think about the James Webb, I think about what we've accomplished. We've built a machine that can see light that's been traveling for over 13 billion years. We've sent it into space to a point 1.5 million kilometers away. We've cooled it down to temperatures colder than outer space. We've aligned its mirrors to nanometer precision. We've calibrated its instruments to detect individual photons. And through this machine, we're seeing the early universe. We're seeing how galaxies formed. We're looking for signs of life on distant planets. We're answering questions that philosophers have been asking for thousands of years. Are we alone? What does the universe look like? How did everything begin? The James Webb is our answer to those questions. It's our way of reaching out toward the cosmos and asking, and the universe is answering back. The light from distant galaxies is reaching our instruments. The photons that have been traveling through the void for billions of years are being collected and analyzed. The secrets of the cosmos are being revealed. This is remarkable. This is beautiful. This is what I find most inspiring about the James Webb Space Telescope. Not just the discoveries it's making, but what it represents about humanity. Our curiosity, our ambition, our reaching towards something greater than ourselves. The James Webb has already exceeded expectations in its early years. It's found things we didn't predict. It's revealed aspects of the universe we didn't know existed. It's forced us to reconsider our understanding of how galaxies form and evolve. And the best is yet to come. Over the next decade, the James Webb will make observations we can't even imagine right now. It will answer questions we're asking today and reveal mysteries we haven't thought to ask about yet. The future of astronomy is being written right now through observations made by the James Webb Space Telescope. Every image it sends back, every spectrum it measures, every discovery it makes is part of that future. We're living in an extraordinary time in human history. We have the technology to observe the most distant objects in the universe. We have instruments sensitive enough to analyze the atmospheres of planets around other stars. We're close to answering the question of whether life exists elsewhere in the cosmos. The James Webb is making all of this possible. It's revolutionizing astronomy. It's changing how we understand the universe and our place in it. And it's only just beginning. Thanks for watching. On June 3rd, 1990, the first images came back from the Hubble Space Telescope. Astronomers gathered around monitors. After spending $1 billion building this machine, after years of delays and technical problems, after launching it into orbit on the space shuttle, this was the moment of truth. This was when they'd find out if it worked. The images appeared on screen, and they were blurry. Not just a little blurry, terribly blurry, completely unusable. The most expensive telescope ever built was broken. A point of light from a star, which should have appeared as a sharp dot, was spread out into a large halo. It was as if someone had put the wrong glasses on the universe. In that moment, the entire Hubble project seemed like a catastrophic failure. Congress was furious. The media was merciless. Scientists who had championed the project felt devastated. Billions of dollars had been spent, and the result was broken. But this disaster, this seemingly impossible situation, became one of the most remarkable redemption stories in the history of science. Because unlike most satellites, the Hubble had been designed with the assumption that it would need to be serviced. And 3.5 years later, a team of astronauts went to the telescope and fixed it. And when the fix was successful, the Hubble transformed from a symbol of failure into the most famous scientific instrument in the world. The Hubble Space Telescope has been operating for over 30 years now. It's made discoveries that have fundamentally changed our understanding of the universe. It's taken images so beautiful and so profound that they've been seen by billions of people. It's inspired generations of scientists and astronomers. And its story, the story of how we built it, how it failed, how we fixed it, and what we discovered, is one of the most compelling stories in the history of human achievement. The idea of putting a telescope in space is actually quite old. In the 1940s, an astronomer named Lyman Spitzer Jr. wrote a paper describing the advantages of a space-based optical telescope. He pointed out that Earth's atmosphere limits what ground-based telescopes can see. If you could get above the atmosphere, you could see much more detail, much fainter objects, without atmospheric distortion. But the technology didn't exist. Rockets weren't powerful enough. Spacecraft couldn't be built reliably enough. Computers weren't sophisticated enough to control remote instruments. The idea had to wait. It waited for decades. Through the 1950s and 1960s, rocket technology advanced. The space age began with Sputnik and the race to the moon. Spacecraft became more sophisticated. Astronauts went to space. Eventually, we built the Space Shuttle, a reusable spacecraft that could carry cargo to orbit. In 1968, NASA began seriously considering a large space telescope project. In 1972, the project was officially approved. It would be called the Hubble Space Telescope, named after Edwin Hubble, an astronomer who discovered that galaxies exist beyond the Milky Way and that the universe is expanding. The concept was ambitious. A 2.4-meter diameter mirror, the largest that could fit inside the Space Shuttle payload bay. Sophisticated instruments to observe the universe, a spacecraft designed to be serviced by astronauts. The total cost was estimated at maybe $400 million in the early 1970s. It would launch in 1983, they thought. Observe for 15 years, revolutionize astronomy. None of those estimates turned out to be accurate. The development of Hubble was incredibly complex. Different institutions built different components. NASA's Marshall Space Flight Center built the optical tube assembly. Perkin-Elmer built the primary mirror. Lockheed built the spacecraft bus. Ball Aerospace built the instruments. Universities and observatories contributed to the science planning. Thousands of engineers and scientists worked on the project over more than a decade. The costs kept escalating. Technical problems kept arising. The mirror had to be ground to extraordinary precision. The surface smoothness had to be accurate to within a small fraction of a micrometer. Getting that kind of precision was difficult. Design changes had to be made. Problems had to be solved. The launch date kept slipping. 1980 became 1982, became 1983. The Challenger disaster in 1986 put all space shuttle flights on hold for 3 years. Finally, on April the 24th, 1990, the space shuttle Discovery launched the Hubble Space Telescope into orbit. The excitement was enormous. This was going to revolutionize astronomy. The images would be thousands of times sharper than ground-based telescopes. We'd see details never before visible. We'd see deeper into the universe. We'd answer fundamental questions about galaxies, stars, the age of the universe, the nature of dark matter. But then the images came back, and they were blurry. It was a catastrophe. For weeks, astronomers tried to figure out what was wrong. They analyzed the data. They looked for explanations. Eventually, they found it. The primary mirror had a spherical aberration. It had been ground to slightly the wrong shape, off by about 2 micrometers across its 2.4-meter diameter. This tiny error was enough to ruin the telescope's performance. How had this happened? During manufacturing, a testing device called a null corrector had been set up incorrectly. This device was supposed to verify that the mirror was ground to the correct shape, but because it was misaligned, it was testing the mirror against the wrong standard. The mirror was ground to match the misaligned test device, not to the correct specification. and nobody caught the error. The cost of this mistake was enormous, not just in dollars, though that was bad, but in prestige. The Hubble had been criticized for cost overruns and delays. Now it was broken. The headlines were brutal. A flawed mirror and flawed management, one NASA report concluded. But here's where the story took a different turn, because the Hubble had been designed with the possibility of servicing in mind. NASA had always known that in space, things can go wrong. So unlike most satellites, which are supposed to work perfectly forever without maintenance, the Hubble was built with the assumption that astronauts would visit it, repair it, upgrade it. NASA decided to mount a repair mission. But how do you fix a mirror that's in space? You can't bring it back to Earth. It's too large and delicate. You can't regrind it in orbit. You have to come up with another solution. The solution was elegant. Install corrective optics. Basically, glasses for the Hubble. A set of small mirrors and lenses that would correct for the spherical aberration of the primary mirror. It would involve a spacewalk to install the corrective optics inside the telescope. It would be one of the most delicate and difficult repairs ever attempted in space. The mission was planned for December 1993. The Space Shuttle Endeavour would launch with 7 astronauts. The astronauts would conduct a series of spacewalks to repair the telescope. They would install the corrective optics. They would replace other components. They would upgrade the telescope's instruments. It was risky. If anything went wrong, if the repair didn't work, the entire Hubble project would be a failure. There was enormous pressure. The entire space astronomy community was watching. On December 2nd, 1993, the Endeavour launched. Over the next few days, astronauts performed 5 spacewalks. They worked outside the telescope in spacesuits at 28,000 kilometers per hour, orbiting Earth. They removed old components. They installed new ones. They installed the corrective optics. On December 18, 1993, the first new images came back from the repaired telescope, and they were sharp, perfectly sharp. The repair had worked. The reaction was euphoric. NASA held a press conference. The images were released to the media. Scientists wept. The public was amazed. Hubble images appeared on front pages of newspapers around the world. The Hubble went from being a symbol of failure to being a triumph of human ingenuity and determination. And what images they were! A galaxy appeared with intricate structure. Stars that had been blurred halos were now distinct points of light. The universe came into focus. In the years that followed, astronauts conducted 4 more servicing missions to the Hubble. Each mission repaired damage, replaced aging components, and installed new, more powerful instruments. The Wide Field Camera 3, installed in 2009, gave the Hubble dramatically improved imaging capability. Each upgrade extended the telescope's life and improved its capabilities. The Hubble was supposed to operate for 15 years. It's now been operating for over 30 years. It continues to make discoveries. It continues to inspire people. It's become far more than just a scientific instrument. It's become a symbol of human achievement, of our ability to overcome obstacles, of our determination to understand the universe. The Hubble observes primarily in visible light and ultraviolet light. This is the light that our eyes can see, or light very close to what our eyes can see. The mirror is 2.4 meters in diameter, large by space telescope standards, but small compared to the largest ground-based telescopes. What makes Hubble powerful is not its size, but that it orbits above Earth's atmosphere, so there's no atmospheric distortion, no blurring from air currents. The Hubble has several instruments. The most famous is probably the Wide Field Camera 3, which takes visible light images. There's also the Cosmic Origin Spectrograph, which splits light into its component wavelengths, allowing analysis of the chemical composition of objects. There's the Space Telescope Imaging Spectrograph. There are infrared instruments. All of these instruments are pointed at the universe, collecting light from distant objects. The light is focused by the mirror, directed to the instruments, detected and transmitted back to Earth. The data from Hubble is processed by computers on the ground. Images are created. Spectra are analyzed. Scientists around the world download the data and study it. Discoveries are made. The discoveries that Hubble has made are extraordinary. Let me talk about some of the most important ones. One of the earliest and most famous Hubble observations was the Deep Field image taken in December 1995. This was a tiny region of sky, about the size of a grain of sand held at arm's length, that appeared to be empty. No bright stars, no obvious galaxies, just blackness. Astronomers proposed pointing the Hubble at this empty patch of sky. Many thought it was a waste of time. Why observe nothing? But the proposal was accepted. The Hubble pointed at this tiny region and gathered light for 10 days. When the images were processed, astronomers were amazed. The tiny patch of sky contained not nothing but thousands of galaxies. Each point of light was an entire galaxy. The deepest field observation ever made revealed a universe vastly more populated with galaxies than anyone had realized. The implications were staggering. If this tiny patch of sky, which represented one part of the universe, contained thousands of galaxies, then scaling up, the entire observable universe must contain billions or trillions of galaxies. The universe was far larger than anyone had previously imagined. The deep field image became iconic. It was seen by millions of people. It inspired people to think about the vastness of the cosmos. It won awards. It was one of the most important observations in the history of astronomy. Following the success of the deep field, Hubble took other deep field observations. The Hubble Ultra Deep Field in 2004 looked at an even smaller region and found even more galaxies. The Hubble Extreme Deep Field in 2012 pushed even deeper. Each observation revealed a universe richer and more populated with galaxies than the last. Another major discovery came from Hubble's observations of the expansion rate of the universe. In the 1990s, astronomers used Hubble to observe distant supernovae, stellar explosions in faraway galaxies. By measuring how bright these supernovae were and how far away they were, astronomers could measure how fast the universe was expanding. The shocking result was that the expansion rate is increasing. The universe's expansion is accelerating. Something which astronomers call dark energy is pushing galaxies apart faster and faster. This discovery was so significant that it won the Nobel Prize in Physics in 2011. The discovery of accelerating expansion changed our understanding of the fate of the universe. We thought gravity would eventually slow down the expansion and reverse it, causing the universe to collapse. But accelerating expansion means the universe will expand forever, getting colder and more empty. This discovery came directly from Hubble observations. Without Hubble, we wouldn't have discovered dark energy. Another major area of discovery has been black holes. Hubble observed stars orbiting near the center of our own galaxy, the Milky Way. By measuring their orbits, astronomers could calculate that there's a massive invisible object at the galactic center, about 4 million times the mass of our sun, compressed into a region smaller than our solar system. This must be a black hole. We call it Sagittarius A star. Hubble also provided evidence that supermassive black holes exist at the centers of essentially all large galaxies. By observing the motions of stars and gas near the centers of many galaxies, astronomers found evidence of massive black holes. This led to the realization that black holes and galaxies are intimately connected, that black hole growth and galaxy evolution are linked. Hubble has also discovered thousands of exoplanets. Well, not directly discovered them. That's usually done by other methods. But Hubble has observed many exoplanet systems, providing data about the planets, their properties, their atmospheres. Hubble has observed star-forming regions. It's shown how stars are born from clouds of gas and dust. It's revealed the details of nebulae. It's shown us planetary systems being formed around young stars. Hubble has observed supernova remnants, the remains of stellar explosions. It studied how the explosion debris expands over time. It's provided insights into the physics of supernovae. Hubble has observed the structure of galaxies. It's shown us that galaxies come in many shapes and sizes: spiral galaxies, elliptical galaxies, irregular galaxies. It's revealed the intricate structure of spiral arms in galaxies. It's shown us colliding galaxies, interacting galaxies, the aftermath of galactic mergers. Every observation the Hubble has made has expanded our knowledge. Every discovery has changed how we understand the universe. But beyond the specific discoveries, the Hubble has had a profound impact on astronomy itself. It's demonstrated the power of space telescopes. It's shown that by getting above Earth's atmosphere, you can see the universe in unprecedented clarity. The Hubble has also had a profound cultural impact. Its images are among the most famous scientific images ever made: the Eagle Nebula's Pillars of Creation, the Andromeda Galaxy, Saturn's rings, the Crab Nebula. These images have been seen by billions of people. They've been printed in magazines, displayed in museums, shown in classrooms. They've inspired people to think about the universe. The Hubble has inspired scientists. It's inspired artists. It's inspired dreamers and philosophers. It's inspired a generation of astronomers and astrophysicists. Many of today's leading astronomers grew up looking at Hubble images and feeling inspired to understand the universe. I think about what the Hubble has accomplished, not just the discoveries, though those are profound, but what it represents about human capability and determination. We had a failure. We acknowledged the failure. We worked together to fix it. We persevered through obstacles, and we succeeded. The repair mission, the moment when the corrective optics were installed and the first sharp images came back, that was a moment of triumph. It showed that humans can accomplish extraordinary things when we work together toward a goal. The Hubble has been a testament to human ingenuity, to our ability to build incredibly sophisticated machines, to our ability to operate them from Earth, millions of kilometers away, to our ability to observe the universe and extract meaning from the light we receive. But now, the James Webb Space Telescope is the new flagship. It's more powerful than Hubble. It observes infrared light instead of visible light. It can see farther back in time, deeper into space. The JWST is the future of space astronomy, but the Hubble continues to operate. It continues to make observations. It continues to contribute to science, and it continues to inspire. Its legacy will endure long after it finally stops operating. The Hubble has shown us a universe of incredible beauty and complexity. It's shown us galaxies, nebulae, stars, black holes, the remnants of supernovae. It's shown us evidence of dark energy, evidence of supermassive black holes, evidence of planetary systems around other stars. It's answered fundamental questions about the universe. It's raised new questions. It's expanded human knowledge in ways that are almost impossible to overstate. When I think about the Hubble, I think about the first time I saw one of its images as a child. I remember being struck by the beauty of it. I remember feeling awe at the vastness of the cosmos revealed in that image. I remember wanting to understand more. That's what the Hubble does. It shows people the universe. It makes the cosmos accessible. It reveals something so profound and so beautiful that it changes how people think about themselves and their place in existence. The Hubble Space Telescope is one of the greatest achievements in the history of human science. Its discovery of dark energy, its images of distant galaxies, its revelation of the universe's vastness and complexity, these will be remembered centuries from now. Future historians will look back at the Hubble as a turning point in human knowledge. And the story of the Hubble, the story of building it, failing, fixing it, succeeding, is a story worth telling. It's a story about human determination. It's a story about overcoming obstacles. It's a story about reaching beyond ourselves to understand something greater. The Hubble has earned its place in history. It's earned the love and respect that it receives. It's earned the inspiration it provides. And it will continue to operate, continue to make observations, continue to contribute to our understanding of the universe. Thanks for watching.